Not too long ago, perhaps a few months ago, I participated in a workshop in which Leslie Valiant, one of the early important contributors to statistical learning theory, gave a talk in the context of pushing the boundaries of artificial intelligence. And one of the topics he discussed is the notion of natural language inference, which is required to resolve questions such as, did Aristotle have a cellular phone? And whether we have the technology yet to do such inference. Now, there are several leaps of inference that need to be made to realize the answer is no for the Aristotle question. First, Aristotle lived, of course, a few thousand years ago and has died since then. And second, cellular phones were invented only recently. Therefore, Aristotle, of course, couldn't have a cell phone in his possession. And such inference was noted to be unlikely to work with existing NLP technology. When the talk ended, during the QA session, someone from the audience mentioned that, hey, actually, if you ask a pre-trained language model to answer that question, he will answer correctly if given the chance. So I'm not sure if he was referring to GPT or some other language model. Valiant seemed rather baffled. He said that this is actually the first time he heard that this is the case, that any natural language system actually answers this question correctly. And this was not just surprising to Valiant, it actually seemed to surprise quite a few people in the audience, including myself, knowing that we are very far in our technology for making such inference. So I thought to myself, is GPT really that good that it can understand such complexities from text? So fast forward, I decided to investigate this. I looked around, I put in some queries of keywords, Aristotle with Cellphone on the web, and it did not take very long to find out there was a page on the web, perhaps several, that discuss a lecture given by Valiant in another institution a few years back, asking the same question. Did Aristotle have a cell phone? And in that blog post that I found, and probably in other pages, there was actually an explicit mention of the line of thinking that would entail that Aristotle did not have a cell phone. It said something like Aristotle lived a few thousand years ago, just the same reasoning that I described to you earlier. So my immediate suspicion was that these pages were somehow used as part of the corpus on which GPT was trained, or whatever model that person tried, enabling it to answer the question of whether Aristotle had a cellular phone quite directly. So in that point, I sighed a sigh of relief in some sense. We still have a lot of work to do in NLP, and it's not a done deal. It appears that the pre-trained language model in this case, just processed the text in a rather shallow way, probably. The text that mentions this question about Aristotle quite explicitly, so that the leap of inference that was required from the language model was not that complicated. So we still got some work to do in NLP and in other fields of AI. So still, with that being said about pre-trained language models, there's no doubt that the most important technology that has recently been developed in NLP is that of massively pre-trained language models such as GPT, BERT, and others that you might have heard of. Pre-trained language models have presented improvements in almost all aspects of natural language processing, including summarization, machine translation, basic inference tasks, question answering, and other tasks. They really do show that there is no data like more data, as the old saying goes. So in a recent thought-provoking opinion paper, two researchers in the NLP community brought to surface a long-standing question that has been lingering in the study of language in NLP, trying to debate the role of pre-trained language models in NLP. So the researchers imagined a scenario in which an octopus is a perfect statistical learner, and that octopus eavesdrops on two stranded people on two separate remote islands, communicating between each other through telegraphs going through the ocean. I know it's a little bit contrived, but hear me here. So since the octopus is a perfect learner, at some point it knows how to intercept messages sent between the people, and essentially pretend to be those two people for each other. And the question is whether the octopus, never having left the ocean or interacting on land, understands the meaning of the communication. So this paper was, in my interpretation, written in criticism of the belief that pre-trained language models will solve all of our problems in NLP and basically generate perfect computational understanding of text. And as I said, while pre-trained language modeling is one of the most important technologies in NLP currently, the paper's final conclusion was that perhaps pre-trained language models are not what's going to get us to actually make computers understand the meaning of language. What we mean by meaning is, of course, up for debate, and you can read the paper for more detail on their perspective, as well as the more traditional philosophical perspective on how meaning is defined. Basically, for now, we think of it as a mapping between language and some domains, such as the real world. So while the question and debate are rather philosophical, trying to relate meaning to form, I think a related question is whether we, in the NLP community, can expect to rely only on pre-trained language models, or perhaps only on text, to perfectly learn language without any grounding of the text in the real world. And to further simplify the question, by grounding, I'm referring to a certain level of interaction with the world, which will be very familiar to you, with senses such as hearing and seeing in the form of videos and audio. So multimodal NLP is where we see significant growth in the NLP literature, and where I think there is a nice alignment and an interface between areas such as computer vision and natural language processing. Each can provide grounding for the other to make better decisions and predictions. So what I want to talk about is, in this talk, is some work that my group has done trying to better understand the connection between grounding of text in additional sources of information, such as video and background audio, and see how they can be used for prediction problems and what they can contribute to such predictions. So I will discuss several projects that we have conducted in the past few years, and I will be very happy to hear the feedback from Vision folks and see exactly what they think about NLP work that has been done, which combines images and video with text. You will see that the vision part of the work, the techniques, processing the images and videos, is rather simplified. So some of it uses current deep learning technology from the vision community, such as the core GRU neural network units. Other than that, relatively we use simple techniques, and I would love to hear some feedback how we can improve on that. So in the first part of the talk, I will discuss a thread of research that we have explored in the recent past in the form of shallow movie understanding. We were posing various prediction tasks that require a certain level of inference to be answered from episodes of TV crime drama. So following this, I will discuss another facet of inference from videos, that of generating text, or in this case, narration for animated videos. This again requires some level of inference, gathering information from three channels: text, audio, and image. So I will conclude with some simpler work that we have done, making use of what I like to think of as a big hammer, canonical correlation analysis, or CCA. I'll describe to you how CCA, which I'm sure many of you probably already are familiar with, can be used for a variety of problems, including generating text from images. At that point, we'll make the distinction between multimodal inference and multiview inference, while multiview inference is slightly different and perhaps encompasses multimodal inference. All throughout the talk, you're more than welcome to interrupt me and ask questions if they come up. So let's first think about where we are with current work in NLP. Okay? Until a few years ago, systems such as question answering and other types of natural language processing inference systems were very shallow in their understanding and ability to understand text or analyze it. However, if we are to think about the kinds of problems and questions that humans deal with and that NLP is very far from being to tackle, they include some missing, incomplete information. The answers require inference, and they also need to be able to accumulate information over time to get an answer. So in this part of the work, we wanted to see how far we can push the envelope in creating a system that tries to handle such challenging inference tasks. We wanted our problem formulation to be such that it can do all of those things that humans do so easily, okay, like situating things in time and space, interpreting dialogue and intentions, being incremental, and going back to the idea of accumulating information as we go along, and finally being able to handle multimodal information. So this is where we thought that the genre of crime drama or whodunits would be a very good fit for this. This genre requires a certain level of inference. We need to figure out with the detective while we are reading the story or watching the show who committed a murder or other crime. And as we go along, we keep updating our beliefs. I'm sure many of you have watched this kind of shows, keep updating their belief about who is the murderer. They try to make guesses and get ideas who is the criminal. On the other hand, the genre is very schematic, allowing us to use it as a good test bed for this kind of natural language multimodal inference I mentioned. It is also very focused. The most important inference problem here is to infer who committed a crime, and that's it. So we further focused on the crime mystery series CSI. So for those of you who are not familiar with CSI, this is a crime drama, American crime drama TV series in the genre of Whodunnit. Over its 15 years of existence, which means we would have quite a bit of data, it has attracted many fans and was selected for quite a few awards in the United States. In the series, there is a fixed team of around 6 detectives. You can see them in the picture over here, and a rather schematic storyline where there are one or more cases that need to be solved through a procedure of collecting evidence, finding suspects, and reconstructing the crime. In the end of each episode, quite close to the end, the criminal is exposed or caught, essentially, and being confronted with the evidence. Our form of using this series was to try and resolve essentially computationally the case as an episode evolves, following human behavior with this show. We wanted to essentially to build what we called a robot detective. So there were 15 seasons of this show, as I mentioned earlier, and we used part of those seasons as our data. Each episode is about 40 to 60 minutes, which means we would deal with quite a long inference task. Each episode, we have to follow the whole episode and think who is the criminal for 40 to 60 minutes. It is not a short sequence inference problem, which makes it more challenging. So how do we define the problem of solving a crime drama, or as we dubbed it, perpetrator identification, identifying the criminal in such a story? So you might be tempted to think that you want to build a model over the entities in the story and try to create a distribution, right, or distribution for the likelihood of each entity behind the criminal. While this is a very natural from a human perspective, it heavily relies on the use of an entity recognizer and co-reference resolution, i.e. identifying which entity mentions refer to the same entity. In addition, the number of entities differ across episodes, which yields problems with evaluation. So we won't do that. Rather than that, we decide to have a more incremental, objective way of identifying the criminal. We have a binary indicator which needs to decide at each point in the caption of the TV or in the screen, in the plot, whether the perpetrator is mentioned in that caption, whether explicitly or through the use of a pronoun. It is true, I agree with you, probably you're thinking it's less natural, perhaps from a human perspective, who does probably create this distribution over the characters in the episode. but it is a good compromise that makes the problem very well defined, incremental in nature, and independent of the number of participants in the episode. So the data that we use is basically movie clips from the episodes of CSI, subtitles for the text modality, aligned with screenplays that help with additional context. We use an alignment algorithm to align the multimodal inputs at the sentence level. Just to give you an idea about the size of the data set, we have a total of 59 number of cases. So we have 59 cases, since episodes can have multiple cases. And the sequences we work with, which are all episodes, can be quite long. Finally, we see that most of the cases are murder cases rather than other types. So the perpetrator identification task or problem actually does make sense. There is always a criminal that commits a crime. You can read more about in the paper about a very interesting case where one of the characters actually committed suicide rather than having a murderer, and see exactly what our system did with it. So how do we actually annotate this data? We annotate this data in two stages. In the first stage, as annotators who watch the video accompanied by the script and the captions, they themselves need to make predictions on whether they think the perpetrator is mentioned. This is done by using this interface that you can see here. So you basically have the captions or the screenplay over here. I hope you can see my cursor. I'm not sure if you can see my cursor, but on the left you can see the captions. Then they have to toggle in between whether the perpetrator is mentioned or not in each caption according to their guess. And finally, they also have to kind of disentangle the cases into which case this kind of caption belongs to. And as I mentioned earlier, the CS episodes often include several cases. That's why they need to do that. We'll talk about that also later, about the problem of case disentanglement. After they're done with annotating the video and watching it, making all predictions, all through guesses essentially, they have to go again through the script, this time knowing who the perpetrator is because they watched the whole episode, and mention the role of all the entities mentioned in the dialogues, whether it's the perpetrator or not, whether it's the suspect or someone else. So they have a choice between perpetrator, suspect, or someone else. As I mentioned, note that at this point, it's more like a labeling task rather than guessing task, because the annotators know who the real perpetrator is at that point. So then they watch the video quite carefully. So we look to see what the inter-annotator agreement was after testing a few episodes with several annotators. Of course, this is the important part, just to see if your task of annotation actually makes sense. You expect to have a good inter-annotator agreement. And we noted that the inter-annotator agreement levels were quite high, relatively high. So that for the case segmentation and annotating the entities after watching the episodes, the inter-annotator agreement is 0.9 or above. For the prediction task, which is done while watching the episode, as expected, the inter-annotator agreement is much lower, around 0.74. But it still shows that humans tend to make similar guesses on who the perpetrator is. So this was about the data and about the annotation and about the problem definition. Now we designed a rather simple model that I will improve on later to solve the task of detecting who the criminal is. So our model is a very simple multimodal fusion model, basically a sequence of LSTM cells at each point trying to predict the perpetrator's presence in each caption. The model takes the three modalities together, and indeed this is where we use the rather simple fusion model that basically took the three modalities, concatenated them, passed them through a linear layer, and then ReLU to get the representation for the multimodal information. So how do we actually process each of the modalities? That's a good question. So for the text, we use something very simple. It was before BERT and all that took off. So we basically mapped the words to glove embeddings, concatenated all the word embeddings, and then passed this through a convolutional layer. So the final dimension of the text input is 255. For the audio, we removed all spoken language sound and kept only music, background noise, and things such as that, but not the spoken language. We extracted MFCCs for every 5 milliseconds and eventually got an audio input of dimension 75. Finally, for the video, we sample one frame from a time step, pass through a pre-trained convolutional neural network called Inception V4 that I'm sure will be more familiar to you than to me, and then use the hidden layers of the CNN as the visual feature detector. So this leads to a video input dimension of around 1500 per timestamp. So just to give you an idea about the setting, what the setting looks like, so we have, as I mentioned earlier, we have 59 sequences corresponding to cases. We use about 10% for development and another 10% for testing. And here are the settings that we used during training. So we used rather a standard training setting where with random initialization, stochastic gradient descent, we trained for 100 epochs, and so on. So what are the baselines we test? This is an important part. We want to be fair. So we test several baselines. The simplest one, with very high recall, just annotate a sentence as having the perpetrator mentioned whenever there is a pronoun in the sentence. So whenever there is a pronoun in the sentence, we think, okay, either it's referring to the perpetrator or the perpetrator is referring to themselves. Then we also use the conditional random fields, or CRFs, where we have a linear model without any incrementality. We make a prediction for the whole sequence per sentence using global decoding as is standard per sequence, as is standard with CRFs. So that's a kind of a more global decoding where you look at the future and the past at the same time. Finally, we also have a baseline in which we use a multi-layered perceptron, or MLP, which makes independent decisions without access to history. So just given the current frame or given the current caption, it tries to make a prediction. So while CRF has access to everything and the MLP has access to no history, the LSTM model we propose is realistic with access to the past, making a step-by-step decision. And of course, all of this is compared against a human that follows the first annotation task, in which a human predicts who the criminal is in an incremental manner. So the metric we report is rather simple. It's basically precision, recall, and F1 of the labels, whether we predict correctly the perpetrator. So you can imagine you have all the gold. I'm not sure if you can see that, but my error. But you have the gold, and you have some zeros. Most of it would be zeros. Some of it would be ones. And then you have the perpetrator model, basically also returning zeros and ones in certain cases. And you just check the overlap between those kind of two columns that we see here in the form of precision, recall, and F1. So results. So let's look at some results on the validation set. So as can be seen, if we just consider the text, both the MLP and the LSTM do quite well compared to the CRF and the pronoun use. So the pronoun baseline is a very simple baseline. You can see it has very high recall. Almost always, whenever there is a mention, it actually gets it, but it gets really hit hard on precision as you would expect, because it makes a lot of false positives. So overall, it doesn't do that well when you actually compare it to the other baselines. And of course, humans have a very high precision identifying the perpetrator. You can see on the right over here, they are doing quite well. But what happens when we actually introduce the other modalities? So in that case, we can see that the modalities do not significantly help in the MLP baseline, but they do help. If you look further, they do help with other models, with the LSTM model, in which the performance significantly improves. This means that the modalities essentially help only when considered, perhaps in conjunction with historic information, or when they are themselves the historic information. Finally, we can see that while the performance with humans is much higher, it is still not perfect, as they are making guesses. So these were the results on the validation set. These are the final results over here. And you can see that the results on the test set are quite similar. Here again, we see that the multimodal information helps significantly, even when we use a simple technique to fuse the modalities, the LSTM. If it wasn't clear, now I realize T stands for text, A stands for audio, and V stands for video. It's for the images from the video. So this is the different modalities combined together. So I can just go through, just kind of let you watch it again when you know now that text, audio, and video stands for TVA, and you can kind of look at that for a second. Okay, so let's look at specific episodes. What we see here on the top is the cumulative distribution over here, the plot on the top, is the cumulative distribution of the true positives as a function of the number of sentences observed for a specific episode called A Night at the Movies. And the number of sentences observed is basically a proxy for the time in the episode that has passed. What we see is that humans are much more hesitant and essentially make very few guesses until much later. In addition, we see that the criminal is not introduced in the beginning of the episode, but rather at a late stage. You can see it from the gold true positives, essentially. So if you're wondering about the pink line in the middle, that's an interesting feature of our annotation. We had kind of a big red button that annotators could press in the middle of the video when they thought that they know now for sure who the killer is with more certainty. So even though they had to kind of guess it with lots of certainty, they could change later their mind, but they really had to press that red button only when they were quite sure. So we see that annotators thought somewhere in the middle they knew who the killer is, but only towards the end realized who it is again and pressed the button. So you can find in the paper several other plots like this, providing details for other episodes. Finally, I want to give you some examples from the LSTM predictions. So what you see here, the intensity of the color indicates the level of the confidence of the LSTM model that the perpetrator is actually mentioned. And the words in blue are mentions of the perpetrator. So you can see when the perpetrator is actually mentioned, the LSTM does become quite confident that indeed they are there, at least in this small sample. You can see that it actually does make sense. So at this point, we were wondering if there is a better way to use the modalities together and fuse them in such a way that better extracts and connects between the video and the text. As you might know, there are several ways to fuse modalities. Early fusion, which is what we did, which just amounts to concatenating the different modalities, and more complex fusion, where there is a specific model that learns the interrelations between the modalities and features and tries to assemble them into a single representation that consists of the information from these modalities. So the method I presented before is more like early fusion, which is a really simple technique. So we further found this nice modality fusion GRU unit called Core GRU by Young et al. This is actually a neural unit that was discovered or invented by your community, by the vision community. It is motivated by the need for learning representations for multimodal inputs when these representations are correlated, for example, because of temporal dependencies. And the unit is basically optimized by maximizing the correlation of the modality representations. In addition, it also uses a learnable model to decide on the effect of each modality on the joint representation. So this basic unit sounded to us like an excellent tool to try in the context of the CSI prediction task. So at that point, we also decided to actually test other problems which we dub as shallow movie understanding related to the CSI task. So as I mentioned, there was quite a bit of information collected during the annotation stage. And some of the collection of data we performed for this dataset represents the ability to understand a specific facet of the episode while watching it. So the first additional task we defined was that of story disentanglement. So basically trying to guess which case each caption belongs to. So basically disentangling the cases from each other. So that was the story disentanglement. The second type of disentanglement we work on is basically trying to see whether we can identify the speaker in the various dialogues in the show. So the episodes are mostly based on the dialogue, and for each speaker we try to determine, again in a multimodal way, whether they are the detective, the perpetrator, or the suspect, or maybe another character. So just to give you kind of the bottom line, here what we see in this set of results is that, again, the way to fuse the modalities is quite important, the way we fuse the modalities. EF here stands for early fusion, like we did with the LSTM model, while MV stands for the use of the core GRU with a special objective function that I won't go into. It doesn't matter for now. And we can see that F1 improves significantly for both the perpetrator identification problem and the speaker type identification problem when we compare early fusion to the core GRU MV style of solving the problem. I won't go into the crime case tagging here. I just wanted to mention it as a problem that kind of runs in your mind, as the results were quite low for both models, even if slightly higher for the core GRU models. It does appear that disentangling the cases from each other in an episode is a very hard problem. For whatever reason, we're still exploring that. Okay. So that's all I had to say about the CSI problem. I want to move to a new problem. Oops, I scrolled by. So the problem that I described to you until now are simple classification problems, regardless of the complex input and inference they require. We perhaps generate intermediate complex representations of the inputs, but we do not generate structured data such as text as output. So in this part of the talk, I want to show you how we can use multimodal information for language generation while still requiring a relatively complex inference. So then the generation that we want to do is from videos into narrations. This means that we insert comments made by a commentator throughout a video to clarify issues in the video. So the video data that we use is taken from a British TV series for children called Peppa Pig. The domain there is very simple, so we can actually focus and hope to solve this problem with current technology. The series follows Peppa, a young female pig, in everyday social, family, and school activities. I think the best thing I can do is actually show you a short clip just to give you an idea on how simple the domain is. So let me try that, to do that. I hope I can share my screen again. Let me just try. I hope you can see the video. Okay.
I'm Peppa Pig.
So I'll skip the introduction.
This is Mommy Pig. And this is Daddy Pig. Peppa Pig. School play.
Peppa's playgroup are going to put on a play.
The Little Red Riding Hood.
Hooray!
All the children have parts in the play. They have to practice at home. Peppa is going to be Little Red Riding Hood. Mummy Pig has made her costume. Daddy Pig is helping Peppa practice.
Okay, Peppa, what do you say?
Yeah, so as you could see, somewhere in the middle, I hope I also heard the sound. I'm not sure if you heard the sound, I realized. But as you could see, somewhere in the middle, there was a male adult voice narrating the scene. So this is the kind of information we want to insert ourselves in our task definition. He said Peppa Pig is putting a costume of Red Riding Hood and so on. So while for the Peppa Pig TV series, it may seem like an artificial task, the motivation is clear. We can imagine using technology which is more developed, for example, to narrate a comment in sports events or otherwise. So we can hope to do that. I want to mention one thing, that while this task that we have defined may seem related to image captioning, it is not quite the same. First, of course, it is done in the context of videos. So it's not just done for an image. However, there is much more to the differences than that. Narrations require articulating more implicit information that appears in a scene or a specific chunk of video. That's what happens with narrations. For example, we may infer from Peppa Pig jumping up and down that she's happy, or from the text stating that she received a new toy, again that she's happy, in which case the narrator could say Peppa Pig is happy. That's actually something that the narrator repeats quite often. In addition, the implicit knowledge may also refer to the physical world, such as absent objects or other types of information. So overall, this problem is quite difficult. And there has been much interest in recent years trying to explore the idea of implicitness in text. And I would like to define this task as basically trying to recover implicit information in videos. And again, this is a very hard task. We cannot hope to fully solve it using current NLP, nor in my understanding using maybe perhaps current computer vision technology. So what I will present is basically a first stab at this problem. So let's talk about the data set that we collected. So we collected around 209 episodes of Peppa Pig. It is important to mention that the videos themselves, the images that we have with Peppa Pig, are relatively simple. They come from vector graphics, as you could see. While we did not have the original studio unrendered videos, we had, of course, the rendered videos, on which we chose to apply similar tools as we did with the CSI data, leading to some basic feature extraction from these videos. I, of course, know this is not ideal to do with such a video. We would hope to have the actual graphics available with a more logical construction, but this is what we essentially had to do given what we had. So we basically split the videos into, We basically split the videos into dialogue and narration parts based on the captions that we had available. The narration was clearly indicated in these captions. So we aligned the modalities at the token level based on time steps. And as I mentioned, extracted features from the videos based on ResNet and MFCC. So actually, to define this problem of narration generation, we split it into two simpler tasks, which we thought are appropriate. The first one is understanding the timing for the narration. So this means we have to identify as the video goes along when the narration should actually jump in and interject a comment. This is slightly different than, say, a sports commentary, which was our original real-world motivation, where narration is actually injected all throughout the video, overriding some of the audio during a game or an event. So in our case, as you could see in the video, hopefully if you heard the sound, and also in the actual episodes, the narrator actually interjects in such a way that halts the rest of the video, and only once the narrator finishes their comment, the video continues. So in this sense, our task of narration timing and unification makes sense. So at the bottom right, you can see the results of with the narration timing task. Over here with the plot. My main point about these results is that yes, grounding the grounding the dialogue in the video and audio does help. As you can see, the multimodal core GRU model does significantly better than simple early fusion multiview model, and that in turns it does significantly better than just using the dialogue, just the text. So this is another point of score for grounding text for inference and generation, grounding the text in videos and audio. The second problem we have to solve, of course, is to identify, once we identify the positions in which to add a narration, is that of actually inserting the text, the narration text. So this is done in our case with the model we call the VIDA, which takes into account the previous dialogue, the video of the part to be narrated, and the future dialogue in the style of an omniscient narrator. So in this slide, we see the results of our Divina model. I won't go into details. You can read more about it in the paper. But you can see that once compared to a strong baseline, it's actually doing quite well. So the retrieval baseline essentially takes the narration in the training data following the dialogue that is most similar to the test dialogue. So basically it pulls out the narration that is closest to the dialogue in the data according to some metric. So we either encode, to do the retrieval baseline, we either encode the test dialogue using CCA or using TF-IDF, and just compute cosine similarity between the dialogue that we are looking at and the dialogue that we have in the training data. Now what we see again is that the use of video information is quite important. Okay. That's all I have to say about videos and grounding in multimodal information in that way. I want to kind of start maybe in a rather anticlimactic way. I want to now describe some simpler work that we have done, where we try to use a general tool like CCA in perhaps an unorthodox way to decode just images into captions. So CCA really is a very simple yet effective tool. It has so many different interpretations and flavors, including an extension in deep learning. It actually dates back to the 1930s. It has a really nice story behind it. And its core, it's a very simple idea. We are presented with multiple views of data instance, and we try to project those two views or vectors into a space such that they're most correlated. So this shared space can be thought to synthesize overlapping information between those two views. So I got intimately acquainted with the technique of CCA, as it serves one of the core basic building blocks in my work about spectral learning of latent variable grammars. Basically, this work focuses on discovering latent variables in parsing data. I'll mention it very briefly later. So I was really impressed by how simple CCA is, yet how many applications it can have in NLP. So I just want to kind of go slowly, in a breeze very quickly on some applications that it can be used for. So the first idea is to have two views, one being a picture and one being a caption for that picture, and to essentially learn the shared space as if it synthesizes the meaning for the picture and the caption. So then, given an image, we can possibly project it into the shared space and then transform this representation further back into a caption. That's essentially the idea which we called CCA decoding. It relies on CCA to perform inference with structured data. So of course, just using CCA to project between image and text space is not as simple as it sounds. The projection of the image is quite easy indeed, but the transformation back into the caption space is not trivial because it's a structured way. It's from a vector back into a structured object. So how do we find such a caption? Caption from the shared space. So here we use a sampling technique, Markov chain Monte Carlo technique, and essentially sample captions based on a phrase table while trying to maximize the dot product between the projection of the caption to the shared space. So I won't go into the technical details, but I also want to mention one more thing. So while the images with the CSI data are real-world images, and as such can be rendered using tools such as ImageNet, the images we discuss here are so-called from the scene dataset, and are rather artificial. So they include a subset of fixed objects and different sizes and possibly different orientations located in a specific background. So in this case, we do actually have the logical representation of the image, which is what we essentially used as a feature vector to represent the image as one view. So that's actually very useful, something we could not use, let's say, with the Peppa Pig data. So here are some results from the image captioning algorithm that I described to you. You can see that there are some predictions from images that are quite suitable and fit the image well. Even if in the cases where the caption is not quite right, in the bad predictions, you can see that at least the captions often identify correctly the objects and the people that are in the picture. So going back to the octopus question that we posed in the beginning of the talk. So let's go back to that. Clearly, grounding text in various modalities can help prediction from that text. The kind of grounding I present in this talk is of course very limited, but I think especially for the CSI work, the point is clear. We see clear effectiveness of this grounding. So at that point, I want to try and think whether multiview and multimodal data is the same, whether we can actually use this idea of combining different informations, different types of information, integrating them together is only done with multimodal information, or we can actually do it in other contexts. And of course, the answer yes is we can do it in other contexts. Because we have run out of time, I had a few more slides that give very short examples of that, so I won't go over that. I'll just mention that you can integrate multi-view information for parsing, where the two views are two parts of a tree. You can do it for deriving word embeddings, where the two views are essentially context and the word occurrence. You can even do it for HMMs, the good old model that people use less these days, where you break a sequence into two parts, essentially, the backward part and the forward part. So there are many ways to actually integrate multi-view information, and multimodal integration is only one way to do that. So I'll stop here and just mention that I see a great future for research in the area of grounding language in vision, and that multi-view and multimodal learning is actually a very powerful idea. So I would be happy to hear your input, and if you have any questions, I'm more than happy to hear. Thank you.